Good morning and good evening to all of you, wherever you are in the world, joining us from where you are. My name is Daniel. I'm an application engineer at Markforged. In fact, I see a few familiar names in the participant list here. So we haven't worked together. My role at Markforged is generally around identifying application fits and helping sort of industrialize those. And I'm joined by Michael. Michael, you want to give a quick intro?
Yeah. Hello, everybody. I'm the VP of Marketing over here at Markforged. I'm currently holed up in a log cabin in Vermont, which is beautiful and safe. And I hope all of you are also somewhere where you are safe and your last couple months have been okay. Really looking forward to chatting today and talking about some of the cool stuff our customers have been doing with our technology.
Awesome. And for better or for worse, one of the things that's shaken out of the everything going on in the world is we have stepped up our game a little bit on the video conferencing side of things. So you may see a flip from time to time. We actually have a printer, two printers in fact, going in the background with a close up on the X7, which is a machine we'll talk a little bit about before we get into all the really fun applications that people are printing with these devices. So what we had in mind for today, so we'll give a quick overview of Markforged, who we are, what we make. And then we're going to get into this program we undertook called 100 Ways We Impact Manufacturing, where we're going to identify some of the trends that shook out from our customer base in terms of how they're using the technology to drive the best business value. And we'll do a deep dive on some of the most interesting applications that exercise uncovered. And we'll definitely look to leave plenty of time for Q&A at the end.
Awesome. So just if you haven't met us before, or as a quick refresher, Markforged, we were founded in 2013. Our headquarters are located just outside of Boston in a beautiful old industrial town called Watertown, Massachusetts. Our founding team met at MIT, and really, I think you can see the pattern of our company. It's Greg Mark, mechanical engineer, loves to figure out how to make the impossible. And then David Benheim, software wonder kid. And it's really the two of them coming together. And I think I hope you'll see today the power of both software and hardware working in lockstep. And that really comes directly from our founders. We're a leader in creating enterprise-grade industrial additive platform. And we're a venture-backed company, and we've been growing pretty quickly, even during the current time period. A little bit of background just on our investors. We've raised over $130 million, have some strategic backers, including Microsoft, Siemens, Porsche, and then Summit is our lead investor. So that's just some background on the company. And sometimes, we don't always brag. Like, a lot of the time we've been kind of heads down trying to build really cool stuff. And here's a moment when I want to brag. We have the world's largest fleet of online industrial printers, which is pretty cool. This map shows you really where they're all lighting up. On our website, we have a blog post tracking the usage of our printing fleet during this last 3 months. And it's been really interesting and really inspiring to watch all of you continue to make things, continue to build, make use of your printers, whether in your manufacturing facilities or back at home. So it's really been inspiring. And we make a platform comprised of hardware, software, and materials all working together to create what we believe is the most robust, smartest, simplest, and ultimately most transformational platform in all of additive manufacturing. And I do want to acknowledge the 3 months we've just lived in. We're strong believers that our technology can help you transform your business and meet competitive market needs. This was already happening before the last 3 months and before this period of Corona. We already know, and I think you guys are very well aware, that in today's world, you don't always win just by being the cheapest, highest volume good or product. There are a lot of other considerations you need in order to win the competitive advantage race. And that's only become bigger deal these last 3 months as supply chains have been disrupted and as consumer demand has spiked. The way that we solve for these problems, how do we deal with this very dynamic world where things change, customer preferences change? We create a platform that we call the Digital Forge. it is hardware, materials, and software all working together. And the goal is to give you agility and responsiveness to solve problems up and down your entire supply chain. And we want to talk a bit about that and show some examples of that today.
For those of you who don't know me, my background is mechanical engineering, so I hope you'll indulge as I quickly geek out over how cool this technology is. So the two printers you see sitting behind me, if you have a view of my camera, are what we call our composite printers. And what these devices do is off of what's called an FFF, or fused filament fabrication platform, which is basically like a super precise glue gun at a little bit broader scale. We deposit a thermoplastic, in our case, a nylon-based thermoplastic called Onyx, and we actually embed continuous fibers like carbon fiber and fiberglass into those parts, lending them the strength that makes them suitable for a set of application spaces that are generally reserved for metals. So as we dive into some of these applications, if they're not metal, most of the stuff we're talking about are composite components that are actually direct one-to-one replacements for what would be traditionally milled on the CNC out of something like aluminum or steel. And then on the other side of the house of our hardware platform, we have a metal printer that from the ground up was designed specifically to be really safe and affordable, opening up the universe of people who could use metal printers by orders of magnitude relative to what was available before. And we'll talk a little bit about how some of our customers actually shifted from previously available metal technology to what we call the Metal X. And here's a quick digital tour of that machine. So you see these spools that are feeding our print head. So what those spools contain is metal filament, so that it's metal powder that's bound in a plastic feedstock material. And that feedstock material renders it safe to use, so you don't have metal particles flying all over your factory floor. You also see this white material that we're depositing. That's a secondary release system that we've built into the system. That you'll see in secondary post-processing. Makes it really easy to remove support material. So as a secondary step, what we do is we put it into a solvent tank that removes a component of that binding system I mentioned, sort of holds or glues those metal particles together. And then from here, we put the parts into a sintering furnace, which first bakes out the remainder of that binding system, and then gets to a high enough temperature to actually diffusion bond those metal particles together, kind of like welding. So the general principle that guides that is materials that weld nicely are generally going to work nicely for this process. And you saw that release layer come into play as we just popped that part off of that ceramic release bed and put it right into the application. So Michael talked a little bit about how we sort of have two halves of the proverbial Markforged brain, one being the mechanical side, the secondary being David's great background in software. And what that empowers is really this unprecedented engine for digital parts inventory. And what this means is I can now store my parts in the cloud digitally and access those parts from anywhere by anyone. So generally, the way our customer organization is set up is they'll have global parts managers that can instantly upload new parts and new versions of parts into the cloud and manage versions and tool paths and fiber reinforcement strategies in the case of the composites printer. And then anyone who would be key stakeholders of those parts, like designers and technicians and engineers, can download those prints remotely from anywhere on the planet. And what this unlocks is this unprecedented level of immediacy, where the idea of printing parts generally is not specific to Markforged, but the level of cloud access that you can take advantage of by accessing the parts from anywhere where you can open a Google Chrome browser is something that's specific to Markforged, which is unlocking this next stage of productivity, where people are designing their entire organizations around this sort of cloud-based parts management strategy. One sort of additional benefit there is with all of these printers that are connected to the cloud, there's nothing stopping us from sending real-time updates to the printers. So if you're already a user of Markforged, you're probably familiar with that little banner that pops up when there's a new firmware update available, or if Eiger got better at slicing your parts, which generally relate to direct improvements in part quality and accuracy.
And one thing that has been, I think, very important to point out is just kind of where we are in the sort of evolution of additive technology. And I think one of the things that we want to point out is, our industry's had a lot of hype. There's been a lot of inflated expectations as to what 3D printing can do. We would all have a 3D printer in our basement. We'd be 3D printing, which, by the way, Daniel here does have a 3D printer in his house, but maybe not all of us will have that in the future. Or printing a car or a helicopter. And I think what we want to point out today on this webinar and the data that we're seeing back from our customers is that our technology is delivering lots of real value today, but it's by working on real tangible problems up and down the supply chain, not on some of those very flashy concepts of print a helicopter. And so we want to zoom in and show you where we're using this technology today and how it's going.
Yeah, that's a great point, Michael, because I think when one of the patterns we see with this 100 Ways program that we undertook is when you start to ignore the types of things that are going to look good on the front of a magazine and start to focus on the things that are driving business value. The organizations that are adopting additive at scale are really aligning the technology to the types of problems that 3D printing is actually good at solving, like distributed manufacturing and digital inventory. So the way they're setting up their organizations actually fundamentally changes. Where we're aligning with the entry point for most, which is a focus on one part and specifically optimizing the cost of that part. What organizations start to find is as they get more advanced with the technology, it's not so much about the part and how it's made, it's more about how it gets there. So impacts like supply chain and logistics start to come into play as some of the key business value drivers. And from there, as organizations further take advantage of that, they can consolidate on those supply chain advantages by reaping the rewards of production agility and responsiveness to problems, thereby improving their designs. And ultimately, we have a couple examples of businesses that are completely reinventing their revenue streams and forging into new lines of business as a result. So to speak a little bit more specifically on what we did here, so my team, the applications engineering team, took about 6 weeks to do sort of a comprehensive survey of our existing customer base to get a better handle on exactly how they're best taking advantage of the technology. So this ranges from Metal X customers to composite customers, and folks all the way up and down the product development cycle, from prototyping all the way to legacy parts management and MRO and spares and stuff like that. So the dominant categories that we saw ended up being things like tools and fixtures. You can see that press brake tool in there, as well as work holding tools like on the bottom right, you can see this laser welding fixture, as well as things like spares and replacements for cars and big industrial equipment. And this really wide range of applications sort of highlighted for us what the scope of possibilities were for our technology. Because one of the themes that we'll talk about a little bit today is we're experts in making 3D printers, but our customers are experts in their domains. So we like to take the time to take the pulse and really listen to what the market is telling us about how the printers are contributing business value on a daily basis. And then at this stage, I'll make a very quick plug. We do have a website with a microsite set up with I think over 100 of these little applications, and you can go in and figure out what specific parts and applications are germane to your industry and what might be interesting to you. But so before I get into some of the actual parts, I wanted to cover off on a couple of trends we saw that were really interesting. So I mentioned before that these composite parts are generally plugging into this sort of elevated application space that used to be reserved for metal. So we saw a nice confirmation of that from these submissions. So the two highest by far, the two highest categories that we saw were parts that were replacing aluminum and steel. Not pictured here. We also saw some titanium part replacements. And then we even saw some replacements for traditional composite fiber. Also sort of an interesting trend we saw, and this one was actually a little unexpected to us because we generally try to keep a pretty good pulse on industry reports and sort of where the industry is headed. And Ernst & Young published this great paper right at the end of 2019 that indicated that end-use parts was going to be sort of the primary category, was going to become a primary category for some early majority adopters of the technology by the year 2022. And we were surprised to find that now in the year 2020, our customers have been living here for years already. So kind of a neat confirmation that this new level of or this new combination of really strong functionally applicable parts, as well as the agile sort of cloud platform, is unlocking this level of productivity that's outpacing what industry experts actually think is possible. Cool. So that said, I'm gonna dive into the applications, and I actually have a bunch of these parts here in front of me, so I'll be flipping back and forth from the slides and my actual camera view here. The first one I'd like to highlight is this really neat fuel nozzle that was developed by Sandia National Labs. And some of you may know Sandia National Labs more for their high profile development of weapon systems and energetics specifically for the Department of Energy. This lab is actually contracted through the private sector to develop more efficient internal combustion engines. So I'm going to go ahead and flip over to my my camera here so you can see this thing a little more closely. Just go. So what's really cool about this thing, so it's got these internal flow channels. So you can see from the back end here, we have all these holes. So these holes actually have a continuous channel that takes some pretty crazy contours to match up with these holes on the top surface here. And what this unlocks for them is this ability to try out really crazy unique geometries without having to worry about the design complexity. The complexity in this case comes free of charge. And to be a little bit more specific about how this is driving value, previously they actually used what's called a DMLS or direct metal laser sintering 3D printer, which is a multi-million-dollar machine that presents some safety challenges that precluded them from actually taking on this technology. So now with this more safe and easy to use platform, they're able to directly print this thing in-house and actually deliver these benefits where for orders of magnitude less cost and lead time, they're able to iterate more frequently and do superior refinement to the designs and try out more parameters in order to deliver more salient results to industry as industry looks to develop the next generation diesel engines.
Yeah, that's the thing that I love the most about this example is like the internal combustion engine, right? Like it's been around since the late 1800s, but you can still make it better. And I think it's like finding ways that you can use new technology to continue to optimize and refine existing processes. Like that is a really interesting example of a use of 3D printing technology.
Cool. So speaking of sort of this trajectory of innovation in automotive, I want to highlight another example that does just the opposite, but in my book just as neat an application. So this is a company called Techron that actually does restorations for vintage racing cars. So like those crazy like Peugeot and Renault and those like classic British racing cars. These guys are specialists in restoring those. And traditionally what they'd have to do is a bunch of really painstaking reverse engineering to go from part to CAD to G-code to CNC. And what they've been able to do with their Metal X is effectively reduce all the parts of that process that were lengthy and labor intensive for their engineering teams. So now they go directly from 3D scanning this legacy part, which for a lot of these legacy parts, the OEM or the manufacturer of that part either no longer exists or they don't support that business line anymore. So they're left to their own devices to figure out how the heck to make this thing from scratch. So what this 3D printer unlocks is basically bringing these parts back from the dead through this process of scanning the part and then importing it into Eiger, which is our software platform, and then directly sending that file to the Metal X printer and getting that part at the time that it's needed, the point that it's needed right away.
Yep. Perfect example of a massive supply chain issue, right? It doesn't exist anymore. There is no supply chain for these parts. You can custom order them, have them custom created. But we've heard from customers like Techron that how disruptive it is to their workflow to have to wait for one of these parts, right? You know, working on a car, they need to determine whether the part will actually work or not. And if they have to go put out a custom order, wait a bunch of weeks for it to come back, it just completely stops their capability of working on these projects. And so this is a perfect use case of taking our technology and solving a really painful supply chain problem.
Awesome. So another kind of interesting supply chain story here, and more from the perspective of just getting parts quickly and responding to customer demands, more so than the actual existential element of it. This is a company called Fisher Connectors, and what Fisher Connectors specializes in is making these really ruggedized and robust electronics connectors for mostly the Department of Defense, with a few medical customers in there as well. And for those who are unfamiliar with working with the government, the way these contracts work is the government submits a public list of requirements to a database, and then any manufacturer can go submit a bid to actually respond to that. And then if you're lucky enough to be selected, then you with that bid, then you go on and produce these things. Now, the challenge for Fisher is what's generally included in those RFQs, or request for quotes, is a POC quantity, or proof that they can actually make a sustained quantity of these. So they'll generally request that manufacturers make a few dozen of these prior to actually awarding the contracts. So that presents a big challenge for parts that are injection molded, like this connector, because injection molding tools generally take months to obtain the actual mold cavities, and it generally costs tens, if not hundreds of thousands of dollars, depending on the complexity of the mold. So what Fisher's doing with their composite printer is actually producing the mold cavity and embedding these parts, these cavities, with a continuous fiber that's designed specifically for high temperature applications, and then shooting these prototype quantities into these cavities. Thereby responding to quotes, and they can generally make these things same day. I'm actually going to switch over here, and I printed this just the other day, and it was just a hair over 4 hours to produce both halves of these. And you can see that the surface quality, it does have those sort of characteristic layer lines that are unique to FDM style 3D printing. However, they don't compromise quality to an extent that actually requires any additional post-processing. So they go directly from print to bolting these into their injection molding rig, and from there they're off to the races. We're responding to these RFQs and ultimately winning more contracts as a result of this heightened level of responsiveness.
Yep. Another great example of a place where I think additive plays really well. I'm a big fan of cables and connectors. I used to work in the audio industry for quite a while. And one of the issues is that even if you have common connectors, a lot of these specialty applications, like especially for military, ruggedization, weatherization, ability to really like drop these things and beat them up, but still have them work. Like there is no place you can go into a catalog to kind of order these types of connectors, right? You really do need to look for a custom solution. And I think this is an awesome use case to say, here's how you can actually meet the need of the market quicker, faster, and beat the competition. So it's a really great example. Daniel, before you go to the next one, we have one question that I wanted you to get to, and then also wanted to just remind everybody, please, as we're going through here, if you have a question, please type it in. We'll definitely get to it either as we go or at the end. Very happy to answer either questions about what we're talking about or really anything you're interested in learning about. The question for you, Daniel, as we're talking about some of the composite materials that we make, do we have any information how these do in vacuum and high radiation environments, specifically questions around use in space?
Yeah, good question. It's really expensive to get stuff into space, so lightweight parts is always an area of interest. So cool news on that front, we do have parts that are actually in the space station today. The exposure to vacuum environments does remain a consideration for engineering because of the fact that being what's called an FFF based platform, it does have inherent porosity to it. And as we start to work with some of the agencies that are responsible for producing these things and industrializing applications, we're learning all kinds of tips and tricks to help mitigate that with some clever engineering strategies. So I'd encourage anyone that wants to learn a little bit more about some of these industrialization strategies to actually go through and check out our website and ask to talk to an application engineer because we do have some experience in this field of industrializing these applications for those vacuum environments. And to address radiation, we haven't actually quantified that, like the max radiation exposure. But generally speaking, the parts were qualified by NASA on both counts with some of those mitigating strategies that I mentioned.
Awesome. Thank you, Daniel.
Sure. Cool. So I want to talk a little bit about this company called PTZ, which is a company based in Germany. PTZ is short for a really long name that I'm not going to attempt to pronounce here today. But so PTZ does really high precision CNC machining work. And one of the capabilities that they have is they actually have these tool collets for their CNC mill that use thermal expansion and contraction to seize and unseat their end mills into this collet. So the process is I put in my new bit, I cool it down to seize it on the bit, and then I can go mill. So that process actually requires a significant amount of cycle time in order to heat and cool this collet. So they've been looking for a while for a solution to engineer a higher performing version of that tool cooler to improve their effective throughput. So they started at milling a block of aluminum. And they actually built this really intricate geometry on the inside of it that allowed for internal passageways for water to go through it. But they found that they couldn't quite get that to conform to the tool body enough to make a measurable difference. So then they went to what's called, I'll mention again, DMLS printing, where they used an ALSIM G4 which has some great thermal conductivity to it. To engineer some of these more conformal and sophisticated channels. And while they were able to approach that geometry, they had some problems with leaking inside the channel. So when they heard that Markforged makes copper, which is actually twice as conductive as aluminum, they went ahead and tried out some of those passageways into this part. And what I'll do here is I actually have this part, so we'll get a little bit of a zoomed in look at it. So I have to really applaud these guys. They did a great job designing for the process with these channels. So they have these water lines that go through these inlets and actually wind around the tool body and get within a quarter of a millimeter of the surface to improve the heat transfer rate, thereby improving their cycle time. So I think they cut their cycle time by about 50%. So really huge improvement in the overall effectiveness of their shop. And one quick note I'll say about copper. So this wasn't always a material that was on our roadmap, but again, I'll mention that's not something that we specialize in terms of like we're not specialists in CNC milling or like high performance electronics or all of the application spaces that end up being like really good fits for copper. But after launching our first couple versions of stainless steel and tool steels, we saw an overwhelming demand for a material that had really great heat transfer properties. So we went ahead and developed copper, which again is twice as conductive as aluminum. So really working out great for things like waveguides, heat sinks, and really cool, sophisticated like heat exchangers like this one.
Yeah, and there's actually we have a follow-up question around copper. Any examples of use in high voltage situations?
Yeah, totally. We have this. Unfortunately, it's not on our website, but we have this super great bus bar part that again, uh, let us know through reaching out on the website. We can send along some pictures and examples of that, and the specifics of the voltage that particular component handled.
Sweet. Thank you, Daniel. Just before we move on to the next application, let's get to a couple other questions in here.
Sure.
Justin has a question. He has a Metal X and is asking about whether or not aluminum is on our roadmap, and I think you have some thoughts around that and also its use cases.
Yeah, totally. So aluminum actually for a time was something that we were scoping out, and we even included in on our roadmap for a while. And so a couple things came to light as we started to industrialize some of these applications for the Metal X. The first being that aluminum has a super narrow window of parameters that allows it to sinter successfully. So we can print aluminum on our platform until the cows come home, but the furnace parameters required a bunch of fine tuning that was really part specific, so it wasn't quite ready yet. So if you're familiar with welding at all, you've probably banged your head against the wall trying to weld aluminum parts before. Similar kind of principle. So to take a full candor, technically it's a big challenge, not impossible, but a big challenge. And then what we started to realize was okay, let's take a look at the universe of parts that aluminum is really suitable for. Number one is aerospace, so parts where aluminum has already been scoped. In researching with NASA, the Air Force, and the FAA, we recognized that we have to go through an entire new qualification process to get that part to market. So if we're going to do that, why not use an even higher performing material like titanium, where titanium generally is more expensive to CNC because it's really hard, but to print where you're just depositing material where it's needed, the cost is relatively commensurate with printing in steel. So that's a better option. And then by no means claiming that we have like the silver bullet to nail every single application, but we found that aluminum was generally used quite a bit in heat transfer applications, not too dissimilar from this tool cooler, where we're actually roughly, I'll say again, doubling the performance of aluminum with copper.
Awesome, and we'll roll through a couple of these that are also related. There is a question here from Michael in the chat. Just how close are we to introducing titanium? We don't have a roadmap update to share today. It is still on a roadmap. We actually have titanium right now that we're in beta, actually trying it out. So it is something we're definitely working on, but we don't have an actual sort of date update that we can share with you today. A couple questions here about the PTC part specifically. Are the collets in this part ready to use as printed or at the end of the sintering process, or is there any post-processing that's required?
Yeah, good question. So for this particular case, they basically in college I had this great professor for thermodynamics, and he called it thermal schmutz. So like if you've worked in these heat transfer applications, you're familiar with this like thermal paste that it's kind of like your duct tape for when things don't fit together very well in contact. So what they do is so the collet obviously being really high precision. We haven't talked a whole lot about Metal X precision, but it's generally kind of like a casting where if you require anything below a couple thousandths of an inch, you're generally going to have to machine that surface. But in this case, I'll take off the camera again just so you can see, you get a better look at the geometry. So it's kind of like this conical surface where they actually just directly seat this on the collet after applying a little bit of that thermal schmutz on the inside of it, and that provides enough of a thermal contact area where they can get all the benefits without having to rely on the secondary process. Quick addendum there. So they do mill out the these little cavities where they have inlets for the hose. So that's the only post processing required, just to get the water lines to have a nice clean seat.
Awesome. And for those of you who maybe haven't used our products before, Eiger, which is our software that really helps you use the entire system, there actually are some specific settings inside of Eiger that you can set if you are going to do post-processing, right? So we can basically make sure the part comes off in a way that will set you up for success, depending on what you want to do after you've printed it. Another question here, I'm going to put you on the spot. I know we have a data sheet and some specs that we can definitely share directly, but there is a question from Hank, but just specifically the CTI value of copper, basically, how actually conductive is this material?
Yeah, I actually have that one off the cuff. It's we do about 400 watts per meter Kelvin. So if you don't have a reference point, that's about double the conductivity of aluminum, or about the same as generally available pure copper.
Awesome, thank you for that. Let's move on to we still have a bunch of questions. Please keep them coming, but let's move on to the next part, and then we'll keep coming back around and answering some of these questions.
Yeah. I hope you guys find this next one fun. I certainly do. So the whole reason I have a part printing on my printer right now, which I'll actually swap to that. On the camera view. So this part is really cool, and so first of all, on a technical level, it's cool. It's applicable to a lot of applications. It's a gear that's actually functioning in end-use capacity. But what this thing is it's a component that belongs to an industrial sandblasting rig, where if you've used these things before, you're familiar with the notion that highly abrasive environment just chews through really, really strong parts, like it's their job. So, which it is. So this company called BMF actually needs to furnish these spare and replacement parts for their customer base. And I'm going to talk a little bit about how they actually go about doing that. Because this is really kind of like one of the biggest transformations in a business model that we saw in the Shakeout of 100 Applications project. So this company BMF, and again another company in Germany that has a three-letter acronym because their full name is difficult for us Westerners to pronounce. So this company, they traditionally used to rely on a supply chain to deliver these parts to customers all over the world, which presented a lot of challenges because not only were their customers really geographically distributed, the consumption of these parts was outsized relative to like traditional spares and replacements parts, and they were generally super heavy. So actually, when they went down this journey, they first started out by saying, okay, I can now print lighter parts and reduce my shipping costs. And then they realized, wait, hang on, these printers are cloud connected, and I can print them anywhere. So they started pushing printers forward to the places where the problems are actually happening by empowering their service technicians with print capabilities geographically distributed all over the globe. And then they realized, hey, wait a minute, I can actually reduce the distance from the point that the part is fabricated to where it's needed at my customer site by actually having printers at my actual customer sites. So now that what they do is they encourage their customer base to go ahead and take on a Markforged composite printer, and they make their database of parts available to their customer base so they can pull down parts as they're needed from the cloud and directly print them where they're needed at the factory.
Awesome. So let's see. While we're on this section 1, can you just confirm, so behind you there printing, that is an X7 printer? Is that what we're looking at?
Yes. Let me go back to my video view here and do so the spotlighted video right now is the X7, which is a really cool machine. If we have time, I'll talk a little bit more about what enables some of those like productivity steps that engineers are able to take with this that are different from traditional FDM style printers. And then I'll go back to my screen here where full picture view here. I have on my left side the X7 and on the right side the Mark II, which is our top of line desktop printer.
Awesome. There's a follow-up question here from Solomon, and just asking, can you print a gear on site without needing the furnace? And I actually think our idea here is that you can print all this on site because we will actually sell you a sintering oven that you can use in your facility. So the part does need, as we saw earlier in the video showing off the Metal X system, we do put it through a wash and then you put it into the sintering oven, but all of that can be accomplished directly on your site. It's safe, easy to use, and is friendly for the kind of environment that you're operating inside of.
Yeah, and then I'll also emphasize that the gears that BMF customers are printing are actually produced on the composite system, believe it or not. So those gears, again, they fulfill the engineering requirements to the extent that they're actually performing quite well in applications where even steel is wearing out.
Awesome. There's a question here from Mark about whether we've ever printed turbo charger wheels. I'm not familiar with what that is referring to. I don't know. Daniel, do you know what that is?
Yeah. Let me reach into my bag of tricks here. I might actually have something. Maybe I don't have it on me. Yeah, it's funny. I actually had one here at some point. Didn't actually have it at the ready here. I'll see if I can dig it up at some point as this presentation continues on here. But yeah, we actually print them in generally prototype capacity. We also have some examples of like water-cooled engine, like those old school Daimler water-cooled engines where customers are actually directly printing those. Quick asterisk, it does require some post-processing to get it to make with the shaft correctly, but yeah, those kind of applications are definitely what I consider sort of inbounds or sort of like within the application space for metal.
Awesome. And I propose a party game where the people in the chat just name random parts and let's see if Daniel happens to have them somewhere in that room with him. I think this will be a fun game. So go for it. Yeah. Pro tip: he has a lot of bicycles, so like see what you can come up with. Kyle asked, and I think you just answered this. What's the material that you're printing that gear with?
Yeah, so in this case, I'm just actually using the onyx material, which I brushed across it, but to really pay off what that is. So it's a thermoplastic. It's a nylon 6 that has chopped carbon fibers embedded in it. So about 20% by mass, in fact, is carbon fiber itself. And that's before we start to inlay the continuous fibers.
Sweet. And while we're on the wheel, just one last one. Can you make worm wheels, specifically in bronze and aluminum bronze with
I think I do have that.
Profiles? Oh, and look what he's got.
Sorry, I cleaned up my desk, which is like I have like the classic engineer's desk with a bunch of parts on it. Oh, darn it, I think kind of close, but I've got this not really that close, but sort of similar. I've got this. Man, we should prepare for this next time. It is fun. But I've got this actual kind of like mating surface with this kind of trigger assembly here. So they interface really nicely and engage. But I do have a one wheel kind of thing. I think brass was mentioned in the question. We actually don't print in brass, but definitely that sounds spicy. I'm interested to learn a little bit more about like how either like thermal conductivity or whatever the application there would be in order to satisfy the engineering requirements with something like bronze.
Awesome, thank you, Daniel. Again, I feel like we're like in a video game. You have a magic bag with just all the possessions you've acquired over the course.
I know. Now I'm like laying out all my parts so that when as we start to play this game of Stump the Scout, I can be a little bit more quick on my toes.
Do we have another application that we wanted to spotlight, or should we keep going with questions?
This actually marks the end of the application section. I was actually just gonna double down on a quick plug to check out all of these applications, because it's actually even more applications than what I have on my desk, if you can believe that. So I'll just go ahead and pop this up on the screen here. Um,
Awesome. Yep. Yeah. So Daniel will drop a link here. So all of these, all the applications we've been talking about today, and a whole bunch more, are available up on our website as part of an application library, which we'll always be adding to. So please come and check that out. We have kind of case studies, some details behind some of them. If any of them catch your fancy, we're happy to go deeper. Reach out to us. We're happy to talk a bit about how the application works, some of the things that we learned in doing it, and whether it's maybe applicable to the kinds of things that you're working on. So please check this out. It's at the Markforged.com. Additive manufacturing movement is the URL there. Let's go through some questions then, Daniel, if that makes sense. A little bit of time
sure.
Here. Sure. So let's see. First up, Paul, who had asked the question earlier about printing parts for space, just lets us know that he's actually considering printing parts for spacesuits, and indeed maybe the gantry of a lunar lander. So his question, very germane. He's actually looking for real live applications there. So that's awesome. And let us know how that goes, Paul. Would love to hear about that project.
Yeah, awesome.
Back on the space track, has there been any HIP work done around the vacuum sensitive parts to reduce some of the porosity in there?
Yeah, good question. So it sounds like whoever asked that question is really well versed in additive manufacturing, and is aware of the fact that with our process, we achieve similar properties to like a casting, where our porosity kind of hovers around 2-3%, depending on the alloy we're using. So that generally precludes it from space as is. Now there are some mitigating strategies that I mentioned we've taken to do that, and hipping is one of the ones that's been investigated, but not actually qualified. For those unfamiliar, HIP stands for hot isostatic pressing. So it's a process where I put it into a big tube filled with little particles, and then I pulse it with a bunch of heat and pressure to get those particles to actually penetrate into the part and take up some of that porosity. So that's well, I wouldn't call it like a par for the course, like easy peasy silver bullet solution. It is what I call a leading candidate solution for mitigating porosity.
Sweet. And on the track of asking around how some of these materials perform in different environments, we have a question around onyx. And do we have any good data on sort of long time exposure to UV radiation and or temperatures in excess of about 110 degrees Fahrenheit?
Yeah, good question. So two-part answer for the two-part question. First part, UV exposure. So while we do see some surface degradation of the onyx with prolonged UV exposure, what we find is because of its opacity, again, I'll just pop up a folio. So the fully opaque surface generally contributes to retaining the mechanical properties underneath. So we've had things like camera mounts that are like for outdoor security cameras and stuff like that, where yes, it did degrade the outer surface, but it retained the overall mechanical integrity of the underlying material. And specifically in that case, we actually had continuous fiber, which is embedded a couple millimeters below the surface anyway. And that being sort of like the skeleton, which we didn't talk a whole ton about the material properties, but it's about an order of magnitude stronger than the polymer itself when we embed that continuous fiber. So that ends up working out really nicely. And the temperature, onyx is generally good up to around 150 C, so like 300 Fahrenheit. So good on that front. And then I also mentioned we have this specialty fiber that's designed specifically to approach those higher temperature applications. So if for one reason or another that we end up thinking about exposing it to even more heat load and temperature, that's generally the strategy we take on.
Well, thank you, Daniel. And again, yeah, if you have specific follow-up questions about any of the material properties, you want to learn more, we're obviously happy to share lots of data, spec sheets, etc. So please reach out and we can share with you like in-depth material around your specific application. But thank you, Daniel, for helping us to answer that one. We have a question here about some of the ways that we print supports for our parts. Eiger, our software, automatically calculates how the supports will work before we start printing. What materials are our supports made in? And do the supports themselves, I think the question is around, do we have sort of the material profiles for those as well?
Sure. Give me one moment. I'm going to answer this in two parts. So I'm actually going to answer the composite version of that and the metal version of that. So hold short. Bear with me. I'm going to do both.
And while Daniel is doing this, I think I'm imagining that we could do like a sort of an hour of with Daniel and his desk. I think would be a really fun webinar topic to follow up in. We basically just ask him random questions and make him run around his room, finding all the parts and showing us things. I think it'd be super fun. So while Daniel is grabbing this part in the back, let's see here. Here he comes. All right, what do you got for us here? Oh, we've there you go.
Cool. So you guys, like we saw as I pulled this part off of the printer, most of the supports actually fell away off of this Onyx part. So the way our support system works in composites is we designed these sort of I actually have a chunk of one here that you can see a little better. So we designed these kind of like accordion style structures that make these little infinitesimal touch points. There's a better view of it. And it's really easy to grab a tail end of this and just kind of rip it out. So that ends up leaving, you can see these teeth actually were all supported because they had, they sort of tripped the overhang constraint that requires that type of support material. So that surface finish actually turns out looking pretty good. Now on the metal side, I actually didn't have a good example, like totally handy. But what we end up doing is we build a metal structure to support it. So we'll actually print a metal body, and then we'll print a thin layer of ceramic that acts as a boundary for physical separation between those two bodies. So when I want to pull that part off, all I need to do is pop it with a hammer, and then it becomes unseated. So this is a little motor mount. I'll show you the sort of like resulting surface for that. And what's great about that is there's no CNC machining or EDM wire type of process required in order to obtain that part and remove it from the support bed. So I'm not sure if the original question was specific to one platform or the other, but figured it'd be good to cover off on both.
Awesome. Thank you for the comprehensive answer. And again, yeah, all of the sort of mechanisms as to how these supports work, our software Eiger really like helps you. It a lot of times will automatically calculate that. You have some choices as well. But again, like, we've really been thinking deeply about how to make this as easy as possible when you go into the printing process. We have a question from Emad, which is around specifically some of the physical properties of the printed metal parts. Does 3D printed metal have a lower yield stress or fatigue life? Is there an effective solution here?
Yeah, so the yield stress is actually elevated slightly above what you'd expect out of a casting. So if that's generally acceptable for your application, then I'd say no sort of additional mitigating strategy required. We haven't qualified yield strength fatigue life up until this point. What we have done is we've qualified a bunch of heat treat strategies, like specifically I'm thinking like for 17.4 stainless steel, like an ASTM 1050 heat treat cycle is great for mitigating fatigue life. But what I'd recommend to that end is again a little plug for our application engineering team. Those guys are ninjas with respect to sort of finding the right sort of like Venn diagram overlap for your technical requirements and our technology fit, along with the mitigating strategies for things like fatigue and yield.
Sweet. Yep. And again, another plug. If you got a question specifically, you want to know if there's a way to do the application you're looking at, yeah, please reach out. Daniel and his merry gang of application engineers are standing by and ready to help. So but please let us know. Let's run through a couple more of these questions. We have a couple more minutes. If you have any last questions, please throw them in here. And we can also follow up afterwards, any ones that we don't get to. We have a question just around the maximum surface area printable through our platform.
Ooh, I kind of want to take that on like super literally and like design something that's optimized for like surface area. Like an example of that would be like this part has a lot more surface area than this part because it has all those crazy internal channels. But maybe the more sort of like topical answer is how big is the print volume? So in the case of the composite printer, we can do pretty close to a cubic foot. So it's 12.5 by 10.5 by 8 is the or I generally think of like, oh, can I print that as like, will it fit in my microwave as kind of like the good wave of the hand bellwether. For the metal, it's a little bit more complicated and specific to the geometry, just because we are using that diffusion bonding process to solidify the part into a solid body. The sort of like wave of the hand size limitation I think of generally today is it about the size of a grapefruit, or maybe on the bigger end, like is it the size of a volleyball, as like the upper bound on size footprint today.
Yeah, from a marketing perspective, that's how we're going to mark the data sheets going forward, is basically just tell you what kind of fruit the object is most likely to resemble, and that's I think that's sufficient for your purpose.
Yeah, get out of here with that watermelon.
I also like the idea of the maximum surface area. That sounds like an abstract math, like topological problem. Like I feel like you could invent it. Yeah, I think you can work on that one and come up with something pretty cool. Related. So there's a question here just around on our roadmap. Do we have a plan for a larger metal print bed? And you know, the quick answer is we can't share right now, confirmed details about our future roadmap. Putting a couple words in Daniel's mouth, I think that there are a lot of very smart ways that you can use the current system to meet many of your application needs. I don't know, how do you think about sort of the size of the print bed of the Metal X and the kind of application fits that you see, Daniel?
Yeah, I'm actually going to go grab a part. Sorry.
So while Daniel was, oh boy, here we go. So you have identified the largest part in the room.
Cool, and I know we're coming up on the top of the hour here, so I'll be brief here. So this is what we call a hybrid part. So this is a really big wrench capable of delivering like 500 Newton meters of torque. And then I printed this wrench socket that is steel. So we've got this sort of like combined body where I actually have these nice little detents where this snaps in really nicely. So understanding full well that this doesn't like capture all applications, it is kind of this nice blend of the two technologies that we have at our disposal to solve engineering problems that require super big parts.
That's awesome. That feels like it's like you're a very small child with a giant toothbrush or something. Like that's a really awesome visual. Thank you for finding that back there.
And talk about new marketing materials we can make out of this.
So we have hit the end of our time, and I think it is we want to definitely keep everybody on schedule. So I think with Daniel holding his largest part in the room, I think we are going to end the session. For those questions that we didn't get to, we will follow up to make sure we have answered all of your questions. Thank you so much for your time. For us, I know at Markforged, this whole process of really surveying and learning about what our customers are doing with our technology has been really fun and exciting. We're constantly surprised by the creativity that we see out in the field and the things that you guys are all doing and the way that you're applying our printers and our platform. Please keep sharing examples with us. Please reach out with any direct questions, and please go visit the application library we have on our website at the Additive Manufacturing Movement URL if you'd like to see more examples and to go deeper on any of the things that we looked at today. So from all of us here at Markforged, thanks again for your time, and we look forward to talking to you and seeing you on an event soon in the future.